If you're working on a wideband RF design, you want your input to be as clean as a super high-end restaurant. While these restaurants might employ a doorman with a list to let in only their clients of interest, the doormen for wideband RF designs are the tunable filters that only let in the signal of interest. To do this, designers have been using large filter banks or complicated analog filters to get the necessary flexibility and performance. But David Mailloux from Analog Devices is with us today to talk about ADI's small, low power, and high performance digitally tunable filters. Welcome to Tech Chats, David.
Hi.
All right, so let's set the stage here. Where and why do we need tunable filters?
So really, tunable filters are used for wideband systems that need to move around in frequency. Particularly, this would be for some sort of listening application or wideband transmitters. So they're essential in many RF and microwave signal chains, particularly for removing the blockers and the harmonics. This is important for wideband systems where the frequency of operation needs to continuously change. The new digitally tunable filters we have developed have excellent RF performance with digital functions. They're easy to use and highly flexible.
Now, you mentioned blockers. Can you explain what those are and why we need to filter them out?
A blocker is an unwanted signal that comes into the system. The problem with the blocker is it destroys a receiver's sensitivity and dynamic range, and it makes it difficult to demodulate the signal of interest. Okay, so what problem are we solving? Shown in this plot is the typical harmonic spectrum coming from a wideband synthesizer. The frequency of interest is 15 gigahertz, but there is significant content in each harmonic of the VCO. Note here that the VCO is operating at 7.5 gigahertz. This could be a problem as it creates unwanted signals in the next stage of a signal chain.
So where would you see these tunable filters used?
So a typical application would be, let's say, an LO signal chain where you have a synthesizer followed by a multiply by 2, and then you would introduce some sort of tunable filter. Another application would be if you had an NCO, and coming out of that NCO, that digital to analog converter, will be some harmonic content, and you want to be able to filter that out.
What have designers been doing in these applications for filtering up until now?
One common solution for needing to jump around in frequency and have a selective filter is a discrete switch filter bank. Shown here is an example, and it really has two single pole double throw switches, and there's 3 filters here. They're just fixed frequency. It often requires large PCB area, and performance is susceptible to the PCB tolerances, particularly the tolerances on line width and vias. The reliability is reduced because we've increased the component count as well, and it's often very application specific. It could be high loss depending on the implementation, and it really requires more system development time. Another solution is analog tunable filters. They're small and compact. They're Varactor-based solutions. Because it is Varactor-based, it usually requires a high voltage, either 15 to 20 volts. And that's typically coming from a DAC or a digipot. And because the Varactor is a nonlinear device, it's susceptible to the noise coming from the DAC. And this results in a phase noise degradation. It effectively phase modulates the signal of interest going through the filter. And then another aspect of this is also the switching speeds can be impacted by the tune voltage settling and the Varactor capacitance. An example shown here is the tunable filter moves from passband 1 to passband 2. Typically, this would be on the switching time would be on the order of, let's say, 2 to 10 microseconds. And typically the noise performance, the baseband output noise spectral density from a DAC would be, let's say, 10 nanovolts per hertz. This would result in a residual phase noise performance coming from the filter of about minus 150 dBc per hertz, which is respectable. But of course, if something lower is needed, then more filtering would be required on that DAC. So with the tuning speed and the noise, of this type of solution, they're really opposing quantities. If you want something very fast, maybe it's not going to have great noise performance. Conversely, if you provided more analog voltage filtering, you could improve your noise performance of the filter, but you will also degrade the settling time, being able to switch quickly with the filter.
Now, let's talk about the digitally tunable filters that ADI offers.
So the new digitally tunable filters that we've introduced utilize an enhanced semiconductor process. We've also employed some industry-friendly packaging techniques, so like a QFN, so typical sizes, 9 millimeters or even smaller. They have low power consumption. They're easy to implement because it's digital. You don't need that DAC solution or the Digipot solution. These are very, highly flexible and reconfigurable. They employ simple SPI logic programming, and some of the digital functionality that we have is lookup tables on the chip for fast frequency hopping. And we'll get more into what we refer to as SPI fast latch mode in the device. The residual noise is excellent as well, and the tuning speed is great. Instead of us applying an analog voltage, now we're applying a control word to move the passband response of the filter. Typically, this would occur on the order of 1 to 2 microseconds, which is a speed improvement over the analog tunable filter, especially if we use this SPI fast latch mode in the device where we use the lookup table.
So with all of these different capabilities and functions, what can designers look for in terms of actual products?
The first product is the ADMV 8818. It is a 2 gigahertz to 18 gigahertz high pass plus low pass filter, and it has an optional bypass mode. Effectively, we have 4 high pass filters and 4 low pass filters, and we can switch out or switch in any filter as needed. So we can create a high pass filter, or we can create a low pass filter, or we can create band pass, all reject, or direct bypass. We can create bandwidths up to 4 gigahertz wide. You could go wider than 4, but then ripple starts to be a concern for some people. But generally speaking, 4 gigahertz would be the widest we would want. Typically, in an application, a wideband listening application, maybe you'd have this in bypass mode. And then when the blocker became present, you would immediately switch in, some filters to get rid of that blocker. Each filter within this product, each high pass and each low pass filter has 4 bits of control. So there's 16 states to adjust the cutoff frequency of that filter. Typical insertion loss is about 9 dB, and the rejection is about 35 dB, 25% away from that 3 dB cutoff frequency. The linearity is excellent, typically 45 dBm, input IP3, and the residual phase noise is typically minus 165 dBc per hertz. We believe that the residual phase noise number actually may be better than this, and that we may actually be limited by our test equipment in the lab to measure this residual phase noise. We're currently exploring some ways of measuring down to minus 185 dBc per hertz, and we believe that this product can achieve that kind of number. The typical power consumption is about 200 microwatts, and the SPI fast latch mode that I mentioned earlier, this is a capability that we have for quickly switching through the lookup table. And how this works is that you would program the lookup table first, and then there's an external pin called SFL. And you bring the SFL pin high, and it enters into the SPI fast latch mode. And then on each rising edge of the chip select bar pin, it will advance to the next lookup table state. And the lookup table state, you can define the start, the stop. You can also define the direction that you're going, whether you're incrementing or you're decrementing. And when it comes to the end, when it comes to the stop, it will automatically roll over. So if you wanted to continually sequence through the same frequencies, the same states, you can do so. The plot shown here is for a constant 4 gigahertz of bandwidth. And the important thing to note is we've combined high-pass filter 1 and low-pass filter 2 to create the first 4 gigahertz of bandwidth. We've combined high-pass filter 2 and low-pass filter 3 to create the next 4 gigahertz of bandwidth, and so forth. So you can really interchange any high-pass filter with any low-pass filter within the chip. The second product that ADI is introducing into the market is the ADMV8913. Each high-pass and low-pass filter is independently controlled and has 4 bits or 16 states. It covers the frequency range from 7 to 12 gigahertz, and it can generate up to 5 gigahertz of bandwidth. It employs the same SPI interface as well as an additional parallel mode interface. This parallel mode interface can be useful if you wanted to quickly change the filter state without needing to write SPI commands to it. This could be used along with, let's say, an FPGA where you quickly toggle GPIOs high and low to fast, frequency hop around. The insertion loss is about 5 dB, and the 35 dB rejection numbers, it's on the low side for the high-pass filter is about minus 20% away, and on the upper end for the low-pass filter, it's about 30% away. Once again, it has the same excellent input IP3 performance, typically 45 dBm. Same residual phase noise performance, minus 165 dBc per hertz, and power consumption of roughly 200 microwatts. And it also has that SPI fast latch mode.
All right, and this next product you have looks like it's maybe a bit of a different setup. Can you talk more about that?
Yeah, the third product that ADI is introducing to the market is this ADMV8052. This is a UHF and VHF tunable bandpass filter that covers 30 megahertz to 520 megahertz. Because it goes so low in frequency, it does encase a larger package. I believe it's 22 millimeters on a side, which is quite large. But when you consider that we are replacing a switch filter bank, which may be many orders of magnitude larger, it's definitely a space savings. The product has an optional bypass mode. Typical bandwidth for each bandpass filter is about 9%. And this is adjustable to, plus or minus 2%. And we have this patented pending interpolation technique for quickly sequencing through the filter states inside the product. This makes it easier to implement the product in a system and adjust the bandwidth and adjust the center frequency as well. The insertion loss is excellent too. It's 4 dB, and that's at 9% bandwidth. If you go to 11% bandwidth, it's about 3 dB. And if you go down to 7% bandwidth, it's about 5 dB insertion loss, which is still pretty good. Rejection numbers tends to be about minus 15%. 20 dB rejection is about 15% away on the low side and 25% away on the high side. Also excellent input IP3, 40 dBm, residual phase noise of minus 165 dBc per hertz, great power consumption as well, and that fast latch mode as well. In summary, ADI's new family of digitally controlled tunable filters provide system designers with highly reconfigurable and easy-to-use solutions for the next generation wideband systems.
Thanks, David. Once again, that's David Mailloux from Analog Devices. If you'd like to learn more about Analog Devices' digitally tunable filters, Click the links in the description or visit Mauser.com. And be sure to check back soon for the next episode of Tech Chats.